Hello and welcome back to MathandBolt. So in today's lecture, we continue our discussion on central forces. Let's have a brief review of what we talked about in the previous lecture. So we started out with the expression of velocity, so that's given by. Then we take this expression and differentiate both sides with respect to time t. So that means we have the rate of change of velocity, which will give us the acceleration. So acceleration was, now if we multiply both sides by the mass m, what we get is the expression for the force. This is the force which is central in nature. So this force is going to be a function of r. So this is f of r, which can be also written as f of r times r cap equals to this particular expression. What we do, we can equate both sides, and that gave us the equation of motion. So we had, now in order to arrive at these two results, we had to use a couple of facts. Let's note them down. The first one was, we had to consider that the direction of angular momentum is fixed. Recall, we got that the expression for angular momentum was mr square theta dot multiplied to r cap cross theta cap. Whenever we say that the direction of L vector is fixed, so that means the motion of the particle is such that it's always constricted to a planar surface. That means motion is occurring on a plane that contains r cap and theta cap. And pictorially, if we understand, it will be simply as shown in the figure. So the particle is constrained to move along this circular path. This is not necessarily a circular path. Whatever path is taken, it's always going to be occurring on a plane surface. Then in number 2, we use another fact that the angular momentum, the magnitude of the angular momentum is a constant, and that's given by mr square theta dot. Now, this was obtained by using the fact that since we have a central force, the central force expression is given by f of r vector is equals to f of r cap, which clearly states that this particular force is along the radial direction only. If there is a force only along the radial direction, that would mean that the torque on the particle is 0. And if the torque is 0, we also know the torque is given by the rate of change of angular momentum L. So whenever the rate of change of angular momentum is 0, that quickly tells us that the angular momentum must be a constant, and the value of this constant is given by mr square theta dot. Then to find the solution to this differential equation, we have to introduce another fact that our energy, the total energy of the system, which is E, and that is going to be a constant. Now together, these two constants, the L, angular momentum L, and the total energy E, are referred to as the integral of motion. Let me write it down. So L and E are referred to as the integral of motion, or sometimes they are also referred to as the first integral of motion. What do we mean by it? So let's use 2 and 3 to get a more clearer picture. So we have from fact number 2 that the angular momentum, which is a constant, is given by mr squared theta dot. So if we write the equation in terms of theta dot, so we have theta dot is equals to L over mr squared. So this is a first order differential equation. So let's box this particular equation for the time being. Now coming to the second fact, we say that the total energy of the system is constant. Now the total energy is comprised of the kinetic energy and the potential energy V. So the kinetic energy is given by half mv squared, whereas the potential is a purely a function of distance r, and that v of r is given by the integral of bringing the particle from infinity to that point r, how much force is needed, so that will be the force vector or the central force, dotted with the radial vector, the elemental radial vector dr. Right. Now we already have mentioned about the expression for velocity. So our velocity was given by, we have v vector equals to r dot r cap. So let's use it right away here. So the magnitude of our velocity vector will be r dot squared plus r square theta dot squared, and that's a square root. If we take v squared, so we'll get r dot squared plus r squared theta dot squared. So we'll be using this in our expression for the kinetic energy. We have half mv squared. So in place of v, we'll have r dot squared plus r square theta dot squared plus v of r, and this is going to be the constant E. Furthermore, what we can do, we can simplify this entire equation and write everything in terms of r dot. So our r dot will give us, r dot will be equals to square root of 2 over m all multiplied to E, the energy, minus v of r minus L squared over 2mr squared. And here we have used the fact that in place of theta dot, we have replaced with it L over mr squared. Right. So this is the expression for r dot. So what we have here, we have now two first order differential equations. So one is in terms of theta dot and another one is r dot. So now if we consider the differential equation r dot equals this particular expression, here we can say that r dot, which is the time derivative of the radius, is equals to, let's say everything is a function of r. So here E is a constant, we have V, the potential function of r, then we have L squared over 2mr squared. L and 2m are constants, so that means we have r dependence here. So this entire expression is a function of r. So we can say that suppose r dot is equals to p of r. Once we have this in particular form, then what we can do, we can separate the differentials to get dr over pr is equals to dt and integrate both sides along with the proper initial conditions. And what is going to give us, it's going to give us the solution r, which will be in terms of function of t. Now once we obtained it, then what we can do, now we go back to our theta dot. So this will be d theta over dt equals to L over m times r squared. So here we can substitute the value of r with the solution that we just obtained. Then we can solve for theta, which will be simply integration of d theta equals to integration of L over m r squared dt, and this is going to give us the solution for theta in terms of a function of t. So once we have the values of theta of t and r of t, then the solution set, let's call it the solution set, theta as a function of time t and the radius as a function of time t. This is going to describe the trajectory of the particle in parametric form, where time t is the parameter. While there is one technical issue, solving the integral dr over p of r equals to integral dt, solving this integral is sort of a technical difficulty. That's because we have this p of r, which is a very complicated expression given by 2 over m. The issue being we do not know the value of the potential function v of r, because this potential function may have some singular value or it might diverge at different values of r. So it won't be an easy task to perform this particular integral by hand. So what we will do in order to have a better insight of the solution, we will try to perform we'll try to find the equation of motion in the form of a relationship between r and theta. That means what we'll try to do, we'll try to obtain solutions for r such that it's a function of theta and not time. In other words, we'll have a time independent form of the orbit. That means the orbit will be given as a function of theta and not as a function of the time t. So in order to find the solution r in terms of the function theta, so we will start with the equation of motion. Now let's divide both sides of this equation with the mass m. So that gives us r double dot minus r theta dot squared equals to 1 over m times the force, which is a function of r. Now we're going to make a substitution here. So we're going to make a substitution that u is equals to 1 over r. Then either we can do this or it's the same thing. I'm saying r is equals to 1 over u. Then we will take the time derivative on both sides, which should give us dr over dt. So that is equals to dt of u inverse, which is equals to -1 over u squared times, we have to use the chain rule, so we have du over dt. So this is our time derivative of the radius r, so this is equals to -1 over u squared. So du over dt, so we can again use the chain rule to rewrite it as du over d theta times d theta over dt. Fine. So this should give us -1 over u squared. So d theta over dt, so that's the time derivative of the angle theta. So that's simply theta dot times du over d theta. So this is dr over dt. We also have from the expression of angular momentum, the theta dot is given by L over mr square. So let's replace this in place of theta dot. So our dr over dt will be -1 over u squared times L over mr squared times du over d theta. So here we have to replace this r with u, and we know that r is equals to 1 over u, so that means r squared will be equals to 1 over u squared, or simply the product r squared times u squared is equals to 1. So we have a product in the denominator. So this is simply -L divided by m times du over d theta. So this is the time derivative of our radius, which is given by -L over m du over d theta. Now again, using this expression, we can obtain the second derivative of r. So what we do, we'll take the second derivative. That means we take the derivative on both sides with respect to time t. So that will be -L over m times d over dt of du over d theta. So on the left hand side we have d squared r over dt squared, which is equals to -L, which is the angular momentum, divided by the mass times, so d over dt of du over d theta can be written as d over d theta of du over d theta whole multiplied to d theta over dt. So this is simply theta dot, so this will get replaced with L over m r squared, and this will become the second derivative of u with respect to theta. So we have negative L over m times, so this is L over m r squared times second derivative of u with respect to theta. So that means this is equals to negative L squared over m squared. So we have r squared in the denominator, so that r should be converted to u. So we have u squared in the numerator times second derivative of u with respect to theta, and this is the second time derivative of the radius r. Now what we'll do, we have obtained r double dot, and we also have, this is our r dot. So let's use this equation to replace it in our equation of motion, this r double dot minus r. So that should give us negative L squared u squared divided by m squared multiplied to second derivative of u with respect to theta minus r times, so we have theta dot squared, so theta dot will be L over m r squared, so r squared will be simply 1 over u, so we have Lu squared over m whole squared is equals to f of r over m. So that should give us negative L squared u squared over m squared times d squared u over d theta squared minus, so here we also have a r, so that will be simply 1 over u times L, so u raised to the power of 4 divided by m squared, L squared equals to f of r over m. 1 u from the denominator and 1 from the numerator goes away, so we have, finally we can take negative L squared u squared over m squared common, so that will be d squared over d theta squared, plus we have L squared u squared common, so u will be in the numerator, u times, okay fine, that's only u, which will be equals to f of r over m. That should give us d squared u over d theta squared plus u is equals to, okay fine, negative m over L squared u squared times f as a function of distance r, but since r is equals to 1 over u, so this the same thing as saying f is a function of u. So this is our new differential equation. So solving this particular differential equation, it is much simpler, and this is going to give us the value of u, which will be a function of theta, and since u is equals to 1 over r, in another way we can say that we have obtained the value of r as a function of theta. Fine. So there is another alternative way of finding the solution u. Let's also mention that. So we have the constant energy is given by the sum of the kinetic energy and the potential energy. Now the kinetic energy is half mv squared, and our potential energy v is a some function of r. Now we have also mentioned here that the rv squared will be simply r dot squared plus r squared theta dot squared plus v of r. Now I've already obtained an expression for r dot, so we have obtained our r dot is equals to negative L over m times du over d theta, and our theta dot, which is equals to L over m r squared. Now if we replace r with u, that's simply if we replace r with 1 over u, then we get L u squared divided by m. So let's substitute this value. So we have, so this is equals to half m r dot squared plus half m r squared theta dot squared plus, So plus v of r, we'll take it to the left hand side. We're left with e minus v of r. Now let's substitute the value of r dot and theta dot into our equation. So we have half m, so r dot squared, so that will be L squared over m squared times du over d theta whole squared plus 1 over 2 times m times r squared. So we have theta dot squared, so that will be L squared u raised to the power of 4 divided by m squared. Fine. So here we have r squared, since r is equals to 1 over u. So we'll have 1 over u squared. So this will be simply 1 over u squared. So that gives us e minus the potential function equals to, so 1m from the numerator and denominator goes away. So we have L squared over 2m times du over d theta whole squared plus half, we have m over u squared times L squared u raised to the power of 4 for m squared. So 1m from the numerator and the denominator, u squared, so this is L squared u squared over 2m. Fine, and we have L squared over 2m times du over d theta whole squared. So that's equals to L squared over 2m times du over d theta whole squared plus we have u squared. This is e minus vr, rearranging the terms, and that gives us du over d theta whole squared plus u squared equals to 2m over L squared multiplied to e minus v of r. So this is another differential equation which will help us to determine the value of u as a function of theta. So this is a non-homogeneous first order differential equation. So we have two differential equations. One is given by d squared u over d theta squared plus u equals to negative m over u squared times L squared multiplied to f of u. And the other one, du over d theta whole squared plus u squared, that's equals to 2m over L squared times e minus v of r. So we'll use either of the two differential equations accordingly, and both of them are going to give us a solution in terms of u as a function of theta. And once we know that, from here we can also find out the value of r. This is essentially the same thing, which will give us the solution of r in terms of theta. So we will end our lecture here for today, and whatever topics that we talked about, the ideas that we talked about in today's lecture, and we'll have a better understanding of it when we pick up a few problems. We'll do that in the next class, which will be a tutorial class. So see you in the next class. Thank you.